Okay, so next talk is from Shaerdan Shataer and Niall McCarroll, both from University of Reading?
Yeah.
Yeah, great. All right, take it away.
Thanks. Thanks everybody. Hi. We're going to talk about a project that was funded by a program called EOSIS. It was running a few years ago, finished in March, and that was to look at climate information, so Earth Observation Climate Information System. And the sub-project that we were involved in is called CHUC, so Climate High Resolution UK. So 100 meters is relatively high resolution for climate data, maybe not for lots of other applications of EO, but 100 meters is reasonably high resolution. Big shout out also to NeoDAS. Thanks very much, guys, for providing the GPUs to train all the models that we built as part of this project. What we're going to do in this talk is we're going to walk you through the process that we followed to model land surface temperatures at high resolution, from defining the model objectives all the way through to doing the validation at the end. And we'll end with a discussion of what could be done differently next time.
So I'll talk about the objectives here. So we aim to build a model that can infer the 100-meter resolution land surface temperature daily, and we want to emulate Landsat 8 and 9. So the context is that Landsat 8 and 9, it comes back every 14 days roughly. So once we learn what Landsat 9 is like, then we can produce daily temperature based on some input predictors. So the predictors are, the input channels are the aerofoil skin temperature, which has roughly 9 kilometer resolution. And then we also have some static or semi-static pattern indicators, such as land cover class. Like for example, whether the place you're looking at, is it rock, grassland, or water. And we have elevation data. We have albedo monthly climatology mean. And also for similar applications, it's very useful to encode day of year positioning to tell so you want the model to know that in certain time of the year what the temperature looks like. And in terms of architecture, we settled with UNet and we customized it and enhanced it.
Okay, so let's take a closer look at the data that Shaerdan just mentioned. So we're going to be using data like land cover, which is very important for driving land surface temperature, elevation, slope direction, slope magnitude. We're also going to be looking at sort of climatological type seasonal averages of how warm it gets, and also how the albedo, so the shininess of the surface, which can influence how it heats up. The thing that we're going to be feeding in that Shaerdan mentioned that does vary is the ERA 5 skin temperature. So that is going to be the thing that really drives the model, and those temperatures will then get distributed over the 100-meter higher resolution grid. We're working on the British National Grid, so as part of the CHUC project, we defined a grid, and we've been building data sets on this grid. So there's a task to certainly get all the data onto this grid, and then we're also getting the Landsat observations. So over here, Landsat 8 and 9. These are level 2 surface temperature retrievals rather than the raw observations. And we want to train a model that can map from these input data to the target for Landsat surface temperatures.
So here's the architecture, and you can recognize the UNet on top. We have it's in this quite several times today now. So you have the encoder part that takes the 12 input channel, and you downsample them, compress, and then extract features all the way down to the bottom layers. We changed the bottom layer from conventional UNet to the conventional UNet use a convolutional bridge for the bottleneck, and we changed it to a fully connected layer because we tested the two and found out that if you use the fully connected one, it predicts the mean of the scene much better. So you get the bottom layer, you get the most efficient representation of the data as a flat vector, and then you take it back through the decoder back to the data space. We also applied this feature channel-wise attention mechanism, which also improved the score by a few percent. So that's the architecture. And in terms of training, we spend most of the time trying to find the best loss function for this problem. The data is incredibly noisy, and we have cloud contaminations. So if you just use the traditional MSE loss, you wouldn't get the pattern very accurate. So we introduced Pearson spatial correlation loss. And once you add that in, the pattern score can improve like 20% or something. We tried Hoover loss as well. Empirically, they say that in multiple literature, they say it's more robust, and it's more robust to outliers, and it generalized better. But in this case, it didn't really help. And we added lots of dropout layers to the fully connected layers, and we use rate decay, batch normalization. These are the regularization, and we apply data enhancement, rotation, and flip, and all that. In terms of filtering, we applied very strict screening process to get rid of the cloud as much as possible, but we did introduce 5% of the cloud so that the thing is more robust. This is the training curve, quite standard, so I'm going to skip that. We had a lot of issues in major challenges, like for instance the low temporal resolutions and persistent cloud contamination, very noisy input. And it's just to clean the data because the noise and signals are quite mixed in both the data space and spectral space. The worst is the last two, that it's very uneven. So you have seasonal scarcity of the data. There are spatial gaps there's disparity between north and south. And when you do have the data of a date, they tend to be clustered around the same region instead of spreading out across the whole of the UK. And if you want to resample, we already have sparse data. We don't have enough scenes. If you want to resample to rebalance them, that reduces the size of the data, so you could probably do that. The next problem is that the pattern generalizes really well. You can learn the pattern really quick, but the mean temperature of the scene doesn't generalize very well. So after each iteration of the model version, we always do a visual check of the whole of the UK. We check the model estimation, and we check some of the specific regions. So the plot here, you can see the input, the temperature input is the error 5. You have 3 or 4 values of that signal for 10 kilometer bar. In the middle is the model estimation, and the rightmost is the ground truth. So the model does learn the pattern pretty well. This is over London, and this is the validation data set. The model doesn't see during training.
Okay, so once we've trained some models, we've picked a model we want to use, we need to design a data product. So what kind of data can we release based on this model? So the data product, of course, contains the model estimates. So this is on a grid that's about 15,000 by 12,000. We're also deciding to include the observation data that we have, that we trained the model on, some information on which boxes we use for training and test, and the ERA 5 skin temperature at the coarse resolution. And in the next slide, I'll explain why we do that. So the idea is that we then do our evaluation on this data product, but also other people can do their own evaluations. We've got some problems here in that the data is has a terrible input bias towards southern England, where it's generally a bit less cloudy. And also, there's a bias in time, so we get less cloud in the summer generally. So, depending on what people might want to use this data in this model for, they're really probably going to like to run their own evaluations depending on the use case that they're considering. Generally, we find that we see much better performance when we consider so-called clear sky test data. So this is data that's less than 5% cloud, very similar to the data we use for training, but from a different geographical area. We see some better performance there. This kind of data would be quite useful for modelling things like heat waves. We seem to be in a heat wave at the moment, so it's quite topical. The all-sky performance, where we're looking at how the model deals with any pixel that's not cloud flagged, is generally lower. And that's because we think there's two reasons, actually, and we're trying to separate the two out a little bit. One is because these pixels tend to be have a higher likelihood of being cloud contaminated. The cloud mask for Landsat is not perfect. And secondly, on a cloudier day, there's less sun falling onto the surface, so there's less insolation, there's less heating. So a model that's trained on largely cloud-free data will tend to overestimate the land surface temperature. Next slide, please. So very quickly digging into the London area. We're looking at just the test data that we collected in London. Rather less data here. For clear sky, we can see that the area distribution is reasonably tight. The model's reasonably accurate. For the all sky model evaluation, we can see that there's a bit of a warm tail going on. So the model is overestimating by sometimes quite a lot. So the model is at the moment better for clear sky use cases, maybe heat waves, urban heat waves, that kind of thing. Can we go back a couple of slides? That one, yeah. One thing that surprised me that I didn't see coming was that the model sometimes hallucinates. So you can see here, these are land surface estimates produced by the model for August 2023, August the 8th, and there's some really cold bits in the middle. Now this can't really happen in real life. So as well as these statistics that we can get comfortable with and spend a lot of time thinking about, there's also maybe thinking about the output as a larger scale and thinking about the kind of physics constraints we might also want to apply to limit this problem.
It's like you've seen the distribution, so the hill could be that the validation data set contains cloud pixels, which the model doesn't know. But we can't be sure. So there's the uncertainty of the validation data itself and also the model performance as well. So these are the conclusion. I just want to emphasize maybe two of them. So one is that we still struggle to generalize the mean temperature, which seems to be a problem. And also another one is currently to counter the cloud problem, we're trying out a few things like incorporating a mask loss function so that the cloud pixels doesn't contribute to the learning of the modeling. And then we also adding extra filtering steps to mitigate out mask errors. Lastly, I think the important one is we can generate a data set that can both gap fill the historical temperature to produce a daily data product, and also we can do like right now, current one, and also in the future if you can have a forecast of the coarse resolution, like the mean temperature of the tech interval. So that's all. Thank you.
Thank you. Okay, we can take questions. Where are they coming from? Steve?
Thank you for that. I just wanted to ask, have you looked at the performance overnight and by day to see how that performs? And also, have you also looked at the regional performance that perform better in certain parts of the UK than other parts of the UK?
Yeah, really, really good question. So for the first part, the model unfortunately can only really estimate land surface temperatures at 11 AM because that's when the Landsat overpasses. I can't remember if it's 10 or 11 o'clock, but yeah, so we can't really say anything about what the temperature is overnight. That would have to be filled in by another model possibly. And then the second question about the regional thing, we have kind of created some regional zones, so Hebrides or the area around Dover, or I think you you came up with quite a few of these. So we are evaluating to see if we're getting consistent performance or if there's if we can see some problems in certain areas. And certainly, we get better performance in southern England at the moment and eastern England.
Okay, I can see two. I think. Do you want to go ahead?
Thank you. Fascinating talk, thank you. You mentioned the issue about hallucinations, and you mentioned the idea of physics-based constraints. And I was just wondering, is that philosophically the right way to go, as opposed to exploring the model architecture and the way you've tuned the model and choices you've made there to try and make a model that learns better and is less likely to do that?
So in terms of architecture, we did quite a few checks to confirm if it's a problem of the architecture. So we used the simpler model, the SR-CNN. I think we had similar problems. We think it's probably less to do with the architecture, but something more inherent with the data set itself. And with this type of issue, if you use more fancier model, it's probably going to amplify.
I think, just to expand on one of your points, I think that the more training data we can get our hands on, the better. So actually, if we just wait a few years, we'll have a lot more data from the two Landsat satellites currently in orbit. We think that the model is hallucinating in those kinds of cases where data is a little bit sparse and the model may be trained with some cloud-contaminated data and it doesn't have a lot to go on.
Yeah.
But that would be, physics-based constraints would only be one solution.
Are there any other questions? Oh, yeah, there are. Okay, well, we're not going to have time for all of them. Sorry.
Come see us afterwards and ask a question.
Yeah, okay, you can come see them after. But we may as well take one more question whilst we change over. So I've seen you first, so I guess this should be you. Sorry everyone.
You mentioned the cloud cover can be a significant challenge, actually, because the training of the model usually happens during a cloudy day, for example, or a clear day, but the prediction could happen in another situation. So could you add the cloud coverage percentage as a separate feature in your modeling that take this into account?
Yeah, we have been experimenting with that a little bit, and also we did quite a lot of work to be able to actually train on cloudy data without messing up the model. So we have been trying to improve that all-sky performance that I noticed. I noted was lower than the clear sky performance.
Just to add, the problem is that we actually had that discussion very early on. The problem is if you increase the percentage of the cloud a tiny bit, it's just very sensitive to cloud for some reason that we're not fully understanding. So if you want to put the cloud fraction as an input, you probably want to increase the range of the cloud so that becomes a significant indicator. And if you do that, you get more noise. The biggest problem is that the cloud mask of Landsat 9 is just very, I don't know if I can say that, it's not very accurate at all for this task. So there are a lot of cloud that's not masked at all. So if you increase the percentage and you increase the noise in the data.
Another thing you can do is, very quickly, is you can try and do a bias correction using the cloudy pixel fraction after the model. So you can take the model outputs and bias correct them using maybe a linear model that considers. But that only buys you a little bit.
Thanks. All right, I think we've got to move on. Let's thank our speakers again.